Now that we've had a look at rational functions and their end behavior, we're going to talk about rational functions and their graphs. So first of all, we're going to go back and review the definition of rational functions. We're going to look at two examples of rational functions and what their graphs look like. We're going to look at for some key features of those graphs, for x-intercepts, for vertical asymptotes, and for some other features of the graph that I don't want to surprise you with now. We'll see that occur naturally as our investigation continues. Alright, so recall the definition of a polynomial. Polynomial is a function with the formula f of x equals constant plus constant times x plus constant times x squared, all the way up to plus constant times x to some highest power n. Again, each of those AIs is a constant. A polynomial only uses addition, subtraction, multiplication to evaluate outputs. If we want to include division, we need rational functions. So a rational function has the formula f of x equals p of x over q of x, where each of those p of x and q of x are polynomials. So as an example, here's f of x with a polynomial on top, 2x squared plus 3x plus 1, and then a polynomial on the bottom, 4x cubed plus 7x squared. Whenever you take two polynomials and divide them, you get yourself a rational function. So what do the graphs of rational functions look like? Well, we know how polynomials work. We have a good idea based upon their roots and the multiplicities of those roots. How do we do this with rational functions? Well, let's look at a relatively simple example, x minus 1 divided by x minus 2. And if we look at that graph, we look at some interesting things happening. First of all, one thing you might notice, right there we have ourselves an x-intercept right at x equals 1. That's not too surprising. If you look at the numerator, if you plug in x equals 1, that numerator is going to 0. And so where the numerator x minus 1 equals 0, that's where you'd expect to have an x-intercept. And then you also have that vertical asymptote right at x equals 2. And again, if you take a look at the formula for the rational function, that's not terribly surprising either. That vertical asymptote x equals 2 happens exactly where the denominator equals 0. Right? Where the denominator equals 0, we'd expect near that denominator for us to have very tiny, tiny values for the denominator. And remember, when we divide by a tiny number, that gives us a huge number. Either a huge number positive if the numerator and denominator have the same sign, or a huge number that's negative if the numerator and denominator have a different sign. Alright, so here's some patterns that we might see. The x-intercepts seem to occur where the numerator is 0, and the vertical asymptotes seem to occur where the denominator is 0. And let's see if these patterns continue if we make the rational function a little more complicated. But one thing it does suggest is that when you factor the numerator and denominator, that helps us understand the function a little bit better. So here's one that's pre-factored for you. I'm not going to make you factor that one from scratch. But we have 20 times x minus 1 times x minus 3 times x minus 4 all over x minus 3 times x minus 5 times x minus 8. So based upon our previous experience, here's what we might expect. We'd expect to have x-intercepts at, well, that's where we set the numerator equal to 0. And that will happen at x equals 1, 3, and 4. Again, that's what we would expect. We'd expect vertical asymptotes, that's where the denominator is equal to 0, and that happens at x equals 3, 5, and 8. Well, let's see what happens in the real world. Well, here's what we get, and it was hard to see, but it's not quite what you'd expect. So let's look at our vertical asymptotes first, x equals 3, 5, and 8. If we look at where the vertical asymptotes actually happen, they do happen at 5 and 8, but something seems to be missing with x equals 3. We'll see if we can figure out why that is true in a little bit. Let's look at the x-intercepts. We expect that at 1, 3, and 4. Now, I have to kind of zoom in because where the x-intercepts happen, it's really hard to tell from the zoom out position that we were. But one thing you notice when you get really close is that, well, we do get x equals 1 and x equals 4, but again, that darn x equals 3 is missing. And now that I think of it, that x equals 3 seemed to happen, or our expectations happened, both in the asymptote and the x-intercept, which might be where we're having our trouble. But in any case, we do get x equals 1 and x equals 4. So what happened at x equals 3? Well, if you look at the original formula, notice that x equals 3 is where the x minus 3 in the numerator equals 0, and the x minus 3 in the denominator equals 0. And since we have the same factor in the numerator and denominator, we can cancel that x minus 3, except we got to remember, when we cancel that x minus 3, we still can't plug in x minus 3. That makes the denominator equal to 0. The function is undefined. But we can't. We got to make sure that function only works when x is not equal to 3. Again, if we put in f of 3 or tried to, we'd end up with 0 over 0, which is undefined. So we do have the graph. We do have a graph with something happening at x equals 3, but it turns out we have a hole in the graph. So if we look at the graph here, now there's something happening at x equals 3. It's just that that point over there where the circle is simply doesn't exist. Alright, so now let's see if you can use this kind of analysis in the graphs that I have you study in intercepts, asymptotes, and holes in the graph. And also there's another one that goes with it as well, that is graphs of rational functions. Both of those will help you understand the graphs, how we graph these rational functions together.